So I will follow my original plan, which was to continue the story. I was talking about the previous days, which was, so let me recall maybe a motivation. So the motivation was to understand examples of these KSBA moduli spaces. And the particular examples we're looking at, you should really think about it as being some example of some kind of, you should think about these moduli spaces as being example of moduli spaces like for the B models of some non-compact Calabi-Yau. So this is some kind of global, like roughly moduli space of complex structure, or moduli space of varieties, so moduli space global B model. So it's a global B model for a specific kind of Calabi-Yau. So for, let me say, non-compact Calabi-Yau. And these non-compact Calabi-Yau, they are constructed starting from, first of all, YD, a log Calabi-Yau pair. First, let me look at the general picture in any dimension. So if you take any log Calabi-Yau pair of dimension D, so Y, like a smooth projective of dimension D, and D some reduced anti-canonical divisor, which is maximal, meaning there exists a zero-dimensional stratum. So we fix this data and the data of L, some ample line bundle on Y. And then, so from the KSBA moduli space perspective, we're looking at pairs of a variety with some divisor. And so here, what we look at will be pairs of the following form, Y and D plus a small multiple of a divisor in the linear system of this ample line bundle. So C lives in the linear system of L. And the reason why it's very natural to do that from the KSBA point of view is because then the canonical bundle of Y plus this divisor, because D is anti-canonical, ky plus D is 0, which is not good for this general theory, because for this general theory you want general type condition like ample log canonical divisor. So we just added epsilon times something ample. So these kind of pairs will be like satisfy the natural higher dimensional version of stability, which is K plus the divisor is ample. And we look at such a pairs when epsilon is positive but very small. And in this condition, the kind of general definition to have semi-log canonical singularities for such a pair, which in general is a complicated condition coming from birational geometry, this complicated condition for such a pair reduces to the very simple condition that this divisor C should avoid the zero-dimensional strata of D. So C could be singular in a kind of arbitrary way. The only thing which matters is that C avoids the zero-dimensional strata of the divisor D. So any such picture is a stable pair in the sense of this KSBS theory. And of course, the collection of such a pairs is non-compact because when C moves, it can hit a zero-dimensional strata. But then by the general theory, something should happen. There should be a new stable pair in the limit. And so we care about the kind of the closure, like I wrote some bar here, which is supposed to be the limit of all possible such picture. And by the general theory, there is a corresponding moduli space denoted by MYDL. So this thing is a kind of KSBA moduli space. and it's a proper, so by the general theory, it's a proper DM stack. So as for stable curves, these general stable pairs have always at most finite automorphism groups. It's a theorem that stable pairs, with the definition again, have finite automorphism groups, so the moduli space will always form like the minimum for stacks.
So D is fixed or is...
Okay, so what is fixed is a decomposition of D into, okay, so I start with such D. Okay, I start with a pair looking like that. So D has some decomposition into irreducible components. And so here in this moduli space, I want to preserve this decomposition. Meaning, in this moduli space, if I have some d tilde, like some y tilde with d tilde, I want this d tilde to have a similar decomposition. So the d's can break, and they will break typically, so I could have more irreducible components, but I don't allow the corners to smooth out. So technically in the moduli space, the data is a y and a d with a decomposition into n divisors, all with weight 1 because I want it to be reduced, and then this extra data. So this thing is like part of the data, which concretely means that, yeah, for example, you are not allowed to smooth a corner of your divisor.
So if you have two P1,
yes,
bring it to 3, but then you can consider two different possibilities. The decomposition can be the first two or the second two. You know what I mean?
yes, that's.
What was it break into more components?
Yeah, that's right. So I think that because here I'm taking the kind of closure of this nice locus.
Yeah.
So indeed, it's kind of part of the data. Like you will know from where it comes from. Like if I have such picture, it breaks, then this particular divisor will break into 2 and so on.
Okay.
So it's really because I come from this nice picture and only look at some kind of natural limits of that. If I consider some more abstract things, it will be indeed less clear what I really mean. So this is.
So Y can also decompose.
Yeah, that's right. Typically, Y will also break into pieces. In the same way that for like usual stable curves, a smooth curve can become a nodal curve, break into pieces. Similarly, Y will break into irreducible components typically. And maybe something which is kind of technical, but will be some technical thing later. So in dimension 1, a curve breaks into nodal curve, so you get like nodal singularities. In higher dimension, Y can break, but it's not necessarily normal crossing. It can break in a more complicated way than normal crossing. And I will say more about that later. Okay. So this thing is a kind of moduli of variety point of view. You care about a variety with a divisor, and you consider this particular class of examples. And the claim is that from mirror symmetries, these moduli spaces are extremely unnatural because the data of such picture, you can think about it as encoding a non-compact Calabi-Yau, which has one more dimension. So from such pictures, there is some corresponding Z, which will be some. Okay, let me give two descriptions of Z. So in the first description, you might, okay. I claim there will be a Z, which will live over this U, which is Y minus D. So the complement Y minus D is like a non-compact Calabi-Yau of dimension D. This thing is like non-compact Calabi-Yau of dimension D. So it's like the interior of this picture. And the Z will be some conic, affine conic bundle over U, which is degenerate over C0, which is like C restricted to the interior. So here is C0 and Z. Okay, I'm mixing a real and complex like picture. So over a point here, I get something like that, and over a curve, I get something like that. So, okay, so here I've not given a full precise definition of Z. Let's recall that last time I discussed a toric situation. So in the toric situation, the YD was just a toric pair. So U was just a torus, which is a torus C star to the n. And C is like, or C0 is like an affine hypersurface, since it's torus, it's defined by a Laurent polynomial. And then CZ concretely is a 3, it's like Calabi-Yau with one more dimension, defined by something like UV equals the equation of this hypersurface, the thing which appear in kind of standard toric mirror symmetry. So here, okay, I want to give a, okay, I want to say what Z is precisely in general, in a way which makes clear it's indeed a Calabi-Yau. So here maybe I cannot write UV equal F, because maybe the line bundle L on the interior maybe is non-trivial. So like I cannot, like this thing is not defined by a function, but by a section of a line bundle, so I might need to be careful. So what is Z? So here is one construction of Z. So I start with, I start with Y of dimension D, and I want to produce something of dimension D plus 1. So I just do the simplest possible thing. I multiply by P1. So here is a picture, so here is Y. And then I multiply by a kind of P1 direction. And I think of this P1 in a toric way. So I have two special points, 0 and infinity. And so in particular, I have a natural like anti-canonical divisor on this variety of dimension D plus 1, which is just like, okay, so I have a, let me write it down. It's kind of obvious on the picture. If I look at Y is times 0, like this thing, union Y times infinity, which is this thing, and then union D times P1, which is like the boundary times P1. This thing is an anti-canonical divisor. Let me call that the boundary of Y times P1. And of course, the complement of this thing is just Y minus D, which I done by U, and then cross C star. So at this point, I did nothing. On the interior, I just multiplied by C star. But now I want to say something. I don't want just multiply by C star. I want to get something ramified over C. And so what I will do is in this picture, look at C. So C is inside Y, and I view C which live in the copy of Y over 0. So maybe here is like C cross 0 inside Y times P1. And so this thing is an hypersurface in Y, but I've added one direction. So C cross 0 is like of codimension 2 inside these extra things. And so I can look at the blow-up of this codimension 2 locus, blow-up of Y times P1 along this C times 0. And okay, so when I do that, I create some exceptional divisor which look like stuff like that. And now to get my Calabi-Yau, I need to remove some anti-canonical divisor. So I will remove the strict transform of the previous anti-canonical divisor. So Z will be this thing, which is like a compact thing. And I remove the strict transform of what I denote by boundary of Y times P1. So this thing is just some like a purely algebra geometric construction of Z. It's an example of this construction. You start with a log Calabi-Yau, you blow up something in the boundary, and you remove the strict transform. And you can easily convince yourself that this thing topologically, or even algebraically, is indeed looking like that. So to go from this picture to this picture, you maybe need to tilt. Maybe I have not drawn this picture in the ideal way. So before blowing up, I have some C stars in the middle. So here are the C stars. Which kind of close up at 0 and infinity. And then when you blow up this curve C, this upper surface in the boundary, you create some exceptional curve. So it's like a P1 bundle over this thing. So you create some P1s. Like that. And then when you remove the boundary, what remains are these kind of degenerate fibers living over C. Okay, so you should, okay, so it's a kind of exercise to clarify that you're happy that this kind of picture is the same as this kind of picture. And again, in toric mirror symmetry, what I've described is one of the standard way to describe this UV equal F thing. Okay. Are there any questions about how do I produce this Z, this D plus 1 dimensional Calabi-Yau non-compact, out of the data of Y D plus epsilon Z? And so the claim is that the moduli space we care about, which is here, from a mirror point of view, you should think about it as some kind of compactified, like B-model moduli space for Z. Because in this moduli space, you kind of vary Y and D, so you kind of vary U. So you kind of vary the complex structure on the U, but you also vary the upper surface C. So clearly, when you move in this moduli space, you kind of move in the moduli space of complex structure of Z. So in general, it may be unclear what is really the B-model moduli space of Z, because Z is like non-compact, and even in cases where it's clear what is a B-model moduli space, what is very unclear in general if there is a natural compactification of this B-model moduli space. And the point is that if Z is a non-compact Calabi-Yau coming from such construction, there is a natural candidate for what is a compactified B-model moduli space, which is provided by this KSBS theory, which is somehow exceptional in mirror symmetry. If I take a random Calabi-Yau, I will not have at least I will not know what is a natural compactification of the B-model moduli space. But if Z looks like that, then there is this guy which is well defined, which is a natural candidate. And so now what you want to do is to understand C space, understand this compactified B-model moduli space.
Instead of Z, like another log pair which
Yeah, that's right. So here you see that, yeah, Z is not just some abstract thing, but by construction, you can think of Z as like an example of a, yeah, Z come as a natural interior of a log Calabi-Yau of one more dimension. So if you want, yeah, instead of Z, you might think about this kind of pair upstairs. That's right. So instead of Z, you might think of this pair. Yeah, the thing I was describing here. So the pair consisting of this variety with this device. So you might think of Z as being like instead of Z, you might replace it by this Calabi-Yau, log Calabi-Yau of one more dimension. And somehow this log Calabi-Yau of one more dimension is not a random log Calabi-Yau, it's quite special. It's obtained from this YD, which is a log Calabi-Yau of lower dimension, multiplied by P1 and blow up one hypersurface in the boundary, which is quite special. In general, like I could start blowing up many things in the boundary to produce many other D+1 log Calabi-Yau pairs, and like other Z's, but they will not be related in a simple way to this picture. In particular, I will not have a candidate for what is a compactified B model module space for them. So yeah, so suddenly there is some kind of inductive structure on the dimension. Like we start with some log Calabi-Yau pair of dimension D, and starting from C, we produce a log Calabi-Yau pair of dimension D+1. But they are kind of special ones. But for almost everything, yeah, like the actual work, mathematical.
Z mapped to U or mapped to Y?
Yeah, Z maps to U.
So the blow up will be plus P1?
So it's important the blob somehow happens at infinity. Which is why I bother to work with this YD, not just with U. Is that to cook up Z out of U, what I do is I compactify U by adding D and producing Y. And then I blow up something in what I've added, which is like C times 0. And then once I blow up, I remove the strict transform of the boundary. So it's like
That is Z, right?
and then I get Z.
Take away that.
Yeah, that's why I remove that. Yeah, that's why once I remove that, then I have a map to U. Yeah, that's right. And then I get this conic bundle picture. Yeah.
So you need D to be maximal, so you need the deepest existence?
Yeah, that's right. So at this point for this construction, you don't need that. This thing is just some geometric. You might try to have a version of it in general. So this thing will matter when you try to, start to understand the nature of this module space and when you try to do mere symmetry. So the kind of general conjecture I was mentioning last time, this conjecture of I can kill you, is that this module space. So here for this conjecture is essential to make this assumption. So under this assumption, then the claim is that this module space should essentially be a toric variety. More precisely, it's like up to a finite, up to a technical thing, but in first approximation, you should think of the claim as being a C thing. And for that, this assumption of having a deeper strata is kind of essential. Yes, this conjecture is for any dimension. Like for example, if you take D to be empty, maybe you look at a compact Calabi-Yau, and there is no reason to expect things like module space of compact Calabi-Yau to be anything like toric. But the claim will be that, for this kind of maximally degenerate log Calabi-Yau, the conjecture says it should be toric. Then you might believe or disbelieve the conjecture, but it is what the conjecture. I mean, definitely, if you remove this assumption, the conjecture is clearly wrong.
Maybe there were results in dimension
2. Okay, so what I will explain is that our main theorem with Valery Alexeyev and here is that we prove this conjecture in dimension 2. Okay, so this thing is conjecture okay, in dimension 2. And essentially most of what we'll talk about today is explaining how do we prove that. So as I will try to explain, already in dimension 2, this statement is highly non-trivial. But of course, you might think that maybe as Conan was mentioning last time, starting from in dimension 2, all log Calabi-Yau's are like rational. Starting from dimension 3, they might not be rational. And maybe you might believe that they're like much further from toric geometry. And you might believe that this thing is a reason to not believe this conjecture. And yeah, I think currently nobody has worked out like a non-trivial, interesting three-dimensional example to really see what's happening.
So interestingly not rational.
Sorry?
Interestingly not rational.
Yes,
Rational.
yes, that's right, yeah. So something I explained last time is that a case where this conjecture is true is that if everything is toric to start with, and maybe in this case it's not so surprising. So if YD is a toric variety with toric boundary, then this kind of statement was stated by Valery Alexeyev 20 years ago, and it's like more or less a consequence of this GKZ story. So in the toric situation, the point is that you can understand what happens at the boundary of this moduli space. What happens is that your toric variety breaks into like smaller toric varieties, and this thing can be described combinatorially in terms of subdivisions of the polytope corresponding to this polarized toric variety. And the combinatorics of this polyhedral decomposition of the polytope can be encoded in a fan, which is a secondary fan. And this thing is a fan of this toric variety. So in the toric situation, you can have a direct B-model understanding of this moduli space. You understand what happens when your variety degenerates in a kind of direct way. And you can see the combinatorial structure of the secondary fan, and you can see you get something toric. But the kind of difficulty with this conjecture is that in general, you don't really know what happens when you go to the boundary of the moduli space. So something which maybe is a reason to not believe this conjecture is that in this toric variety, there should be very particular points, which are like the torus fixed points of this toric variety, which should be some kind of large complex structure degeneration of this variety. And I will be more precise what do I mean by that in dimension 2. And it's even unclear if inside this moduli space, if there is any point which looks like a natural candidate for what will be the kind of maximal degeneration. And I will explain in dimension 2, finding such a point is like the starting point of the story, where you can try to do mirror symmetry if you have a large complex structure. Maybe in higher dimensions, there are such things which are like maybe analog to rigid Calabi-Yau, compact Calabi-Yau, which do not have I don't really know. So here, from a B-model point of view, the difficulty is understanding the boundary of this moduli space. And this thing is not clear at all. And so for example, it's not clear whether the zero-dimensional strata. And if you have a projective toric variety, there is something remarkable, which is if you have two zero-dimensional strata, you can always connect them through P1 toric strata, if you have a projective variety. And which means that these maximal degeneration points, they should all be connected by some kind of simple moves in the kind of boundary of the moduli space. And even in dimension 2, I don't know a kind of elementary proof of this statement. And actually, if you think so here the statement, the way I phrase it is quite vague. Yeah. But actually, even in the toric case, you can phrase it in a way which is not fully trivial. In the toric case, here the purely combinatorial statement, if you take two, I have a polytope, and I take two regular triangulations. So this thing is a regular triangulation, and this thing is a regular triangulation. The statement is that they can be connected by a sequence of flip of the triangulations, which at every step remains regular. Where regular means that this triangulation is some kind of the domains of linearity of a convex PL function. So the fact that two random triangulations are connected by flips is kind of obvious. Maybe in dimension 2 it's really obvious. But the fact that you can do it such that at every step it remains regular is not obvious. And so of course, if you read the JKZ book, then it follows from the theory of the secondary fan that is true. But yeah, definitely if you know some a priori like geometric reason for why it should be true, I would be very interested because then there would be a hope to maybe have a like more B-model understanding of the conjecture. So yes, I don't have a B-model understanding of that, but on the A model, there will be a statement that two quantizations are related by flops, like very simple kind of flops, and this thing would be some general MMP birational geometry result. So from the B model, this thing is kind of mysterious, but it will be clear on the A model. Okay, so there are these things which are unclear. If it is a toric variety, what are the zero-dimensional strata, what are the one-dimensional strata? And what is also very much unclear that if there is a toric variety, it means there is a big torus inside this, roughly inside this moduli space. So there is a big locus, which is roughly a torus. And you can ask, what is this locus, which is supposed to be a torus? And this thing is also not clear. So you might try to guess the naive thing that maybe just a locus where this thing is irreducible, is a kind of natural interior of the moduli space. And maybe this thing should be the torus, but this thing is not true. And actually, even in the toric situation, it's not true. Actually, I wanted to do a very basic example, which is related to Michel's talks, which is just a toric situation for local P2, which I guess many of you might know, but you just rephrase it in this language. So here, still purely toric. I start with a polytope, which is so here is a polytope with vertex 1, 0, 0, 1, minus 1, minus 1. This polytope corresponds to some toric variety Y with some toric boundary D with some line bundle. And I think this thing is what Michel described. It's true that Y is some P2 divided by Z mod 3. And this D is T is the toric boundary, and L in this example happens to be the canonical, anti-canonical, anti-canonical of Y. And okay, so this thing is a picture. So this polytope is really a picture of this toric variety. The toric variety is a torus aberration over this thing. And you have this curve C, which is kind of dual to. And despite the picture, it has intersection number 1, 1, 1 here. It's a transverse intersection. It's like a genus 1 curve. And so what happens in this moduli space? In this moduli space, just the elliptic curve is moved in the linear system. And in this case, the moduli space is actually of dimension 1. And the secondary fan is correspondingly one-dimensional. So the secondary fan in general, its dimension is like the dimension of the secondary fan is like the number of integral points in the polytope minus the dimension minus 1. And here the number of integral points is 1, 2, 3, 4. The dimension is 2. We're looking at surfaces. Minus 1, so this thing is 1. And in general, the maximal cones correspond to the various triangulations of this polytope. And so I have a triangulation which looks like that. And so it's a kind of triangulation in X, and I have a triangulation which is just a triangle itself. This thing has only two ways to write this lattice triangle as a union of like lattice triangle. Because it's already a triangle, there is a trivial subdivision. And then there is this division where I divide the big triangle into these three smaller triangles. And so what the general theorem is telling us is that in this case, the moduli space MYDL is a toric variety with fan given by this picture, which is just a fan of P1. So maybe here I drew some kind of complex version of P1. And I have kind of two special points. And so over a random point, I have my toric surface, and I have this genus 1 curve inside. And what happens here, so at the point corresponding to this cone, I have these triangulations, which means concretely that my P2, not P2, the surface Y will break according to this picture. So it will break into a union of 3 irreducible components. And each of these irreducible components is a P2 because this triangle of size 1 is like the momentum polytope of P2 with line bundle of 1. So which means this curve also breaks, and it breaks into a union of lines. So this point is like a large complex structure limit point from every possible definition. So in this toric situation, these large complex structure limit points correspond to triangulations into triangles of size, like the smallest possible triangles. And indeed, here, like everything breaks into pieces. And for example, yeah. Whereas here, so what is this point? Actually, because this thing remains a triangle, actually nothing breaks here. So nothing breaks. And so you might ask, what is this point? So actually this point here is like inside the naive interior of the moduli space. If you just look at pairs where the variety does not break, this point is actually inside it. And if you look what is this point, like what is special about this point, so actually at this point the curve is smooth, but it's exactly the curve which has a Z mod 3Z automorphisms. So I think this curve is exactly this x cubed, it's exactly this Fermat thing, which has, so this pair actually has an extra Z mod 3Z automorphism. So in some kind of standard mirror symmetry context, this thing will be called an orbifold point. So in this kind of picture, the orbifold point is like inside the toric boundary, which is maybe confusing. And something related, something which is also confusing, which is usually maybe from a mirror symmetry point of view, you want to think of the place where C is smooth. You want to be away from the discriminant locus. So here there is a point, maybe here. Okay, so this point is like of a different nature. It's not a toric. So there is a point somewhere where the curve becomes nodal, which in usual mirror symmetry is like a conifold point. And maybe usually you think of the conifold point, or more generally the discriminant locus, as not really being part of your moduli space, because the Calabi-Yau there become kind of singular. You think about it as being part of the boundary. But here in this case B picture, what is called the boundary and what is called the interior is kind of different. In particular, if you just know this geometry, some of the claim is that, okay, you remove this large complex structure, you remove this orbifold point, then the complement is a C star. And this thing is a C star which gives a toric structure in the base. But which is like, but this may be unclear, how do you guess this C star from the beginning? So actually, okay. So let me correct this statement. I mean, in the toric geometry, let me give the answer what is a C star to the n, because this thing will be useful. It's a useful thing to know. So in the toric case, so Y is a moduli space. Okay. So if you ask the question, is a moduli space toric, as the first question you can ask, can you find a torus inside? And so in the toric situation, Y is a torus inside. So in toric case, so what is this torus inside this moduli space? So in the toric situation, you only move your hypersurface. And your hypersurface in the toric situation is defined by a Laurent polynomial. And so it just have an equation of the form sum over some monomials, some coefficients, v to the m equals 0. So in other words, what is crucial in the toric situation is that if you look at the space of sections of an ample line bundle on a toric variety, this space has a canonical decomposition. And in the toric situation, it's not surprising because the torus acts everywhere. So there is some eigenspace decomposition of this space, and the eigenvectors are just the monomials. So for every integral point in your polytope, there is a corresponding monomial. And this thing gives you a basis. So here in this example, it's just what Michel was writing down. There is like 1xy, 1 over xy. So the general equation is like some constant plus constant times x plus constant times y plus constant divided by xy. And so you see there is an obvious torus. So because there is this canonical basis, so the point is that here there is a canonical basis, you can define the obvious torus by asking all these coefficients to be non-zero. So if you look, so this thing would be the locus where the coefficient Cm is non-zero for every m. So here there is something non-trivial to check, which at the end of the day is trivial, but that you need to check a priori. You need to check that if this condition is satisfied, then you are indeed inside this moduli space. That indeed this curve, or this hypersurface, is avoiding the zero-dimensional strata of D. But this thing is some elementary toric geometry that if the coefficient corresponding to the monomial corresponding to a vertex of the polytope is non-zero, then when you restrict this equation to this torus fixed point, you just find this non-zero coefficient, so this thing does not go through the corner. So what is non-trivial is that this thing is contained, actually is not only contained in, okay, so what is always true is that this torus is contained inside the naive interior of the moduli space. So inside this kind of, like this locus, what I'm doing like the locus of pairs where the thing is reducible. So it's always inside, but typically it's smaller. Even in this kind of trivial example, the kind of naive interior of the moduli space is everything except one point, but this C star is everything except this orbifold point. So the key point here is one way to abstract what's going on is that the space of section of an ample line bundle on a toric variety has a canonical decomposition into one-dimensional subspaces. So you can write the equation of your hypersurface in this basis. And this basis has this remarkable property that if all the coefficients of the basis element in the equation is they're all non-zero, then the corresponding hypersurface avoids the zero-dimensional corners. This thing is a kind of like property of the monomial basis on the toric variety. So if you want to like state a kind of stronger version of this conjecture, the prediction is that if you take any ample line bundle on a log Calabi-Yau surface, somehow there should be a canonical decomposition of the space of section into one-dimensional spaces. There should be some kind of canonical basis. And the key point is that canonical basis should have this property that if you write your equations as a linear combination of basis element with all non-zero coefficients, then the corresponding hypersurface avoids the zero-dimensional strata. So this thing is like a kind of more precise statement which at least implies that there is a torus in the moduli space. And currently, as far as I can say, there is no B-model understanding of why the space of a section of a ample line bundle on a log Calabi-Yau pair should admit a canonical basis. So probably it's not fully true. So there is some. Let me not digress. So there is some heuristic picture which goes back to Turing, which has to do with like geometric quantization of integrable system, which should lead to such canonical basis, but there is currently it's not understood how to realize it, as far as I can say. So in our story, the way this canonical basis will appear in the non-toric situation will come from mirror symmetry, will come from the A model. Yes?
Questions? To clarify, so here you describe this KXPA moduli space. Now, we did say that, well, okay, you made some comments. So now there's also moduli space for the non-toric for the Calabi-Yau, sorry, for the Z.
Mm-hmm.
And there's also moduli space for like these C's.
Yeah.
Now, so is the claim that we expect them to always be the same, but there's like a different kind of boundary decomposition, or what is the claim?
Yeah, I don't know. It says moduli space by definition is a kind of moduli space of this pair, like C inside YD. And I would just take that as my definition of the moduli space of Z. So I can always make this conic bundle construction over that.
Okay.
So for me, there is only like one.
There's only one.
One.
Oh, okay. And then it agrees with all the moduli spaces we know, except that there's a different boundary distribution.
Yeah, that's right, exactly. Yeah, yes.
And then sorry, then maybe they just ask also on the A side, just
yes.
Or maybe that's going to be the next thing you're going to tell us about.
Yeah, that's right. And it's true we started at 30. Maybe it's actually a natural place to stop.
Yeah.
And then I can continue afterwards. And then indeed the next thing to do is I will start to say something on mirror symmetry on the A side, which will be where the work will actually take place.
So is this space, this particular example,
Yes.
is this the special K now?
Yes, that's right. So it's like the stringy K moduli space of the mirror, which is just local P2. I will say that. Maybe I should say that now. Well, I don't know. So the mirror to this geometry is one way to describe it is to take this polytope, take the cone over it. It's a fan. And if you look at the corresponding toric variety, you get the affine singular toric variety, which in this example was described in Michel's talk is C3 mod Z3. And this is a choice of triangulation correspond to a Crepont resolution of that, which produce local P2, so the total space of the canonical line on P2, and this thing P2 is contracted to a point. And the claim is that this secondary fan is sometimes called the Mori fan of this relative geometry. There's some kind of Keller moduli space. And indeed, so Kp2 has a kind of Keller moduli space, which is a Keller class of P2, which produces this cone. And then when you go there, the volume of P2 shrink to a point. So you get this orbifold guy. And from a geometric point of view, if you think in a naive algebra geometric way as an F cone of this thing, you will say, oh, it's just a point because there is no divisor in this thing. It's just an orbifold point. And so there is a general recipe to attach to this thing a cone, which is still maximal dimensional, which is that this geometry is obtained from another one by contracting a divisor. And so the general recipe is to take the F cone of this guy, which in this case is trivial, it's just 0. And then you add to that the class of the divisors you contracted to produce this geometry. And if you think about where is the class of P2 inside the H2 of P2, it's like -3 with respect to the natural basis. So it's really sitting, so here there is some kind of -3. Okay, so let me try to say it properly. So this thing should be the class of P2 inside H2 of Kp2Z, where here the 1 is like the class of a, essentially the class of a line. So this thing can be identified with H2 of P2. And so this thing has an obvious generator, which is just like the line in P2. And I claim that under this identification, this divisor and this threefold through this isomorphism becomes -3. It essentially, it's like a normal bundle calculation, just, yeah. And so So the recipe to produce this extra cone is you take the nth cone of this kind of orbifold guy, which is trivial, which produces a cone which is too small to be a maximal dimensional cone, but you add the classes of the divisors you contracted to produce this geometry, and then you get back a maximal dimensional cone. It's something that Shankil called a bogus cone. And I think they're kind of bogus because they're kind of reconstructed in some way from the other cone. It's like, here there is like the honest Keller cones, and in general there might be many of them related by flop. And when you go to the boundary, there is things where you don't get flop, but divisors contracted. And this is where you can go beyond this boundary by just adding these classes of divisors being contracted. And it is a theorem that if you do that, at the end you get a complete fan. So I'm pretty sure there should be some kind of orbifold reformulation of what this cone is. I think if you think what is like the orbifold Keller cone of this thing, probably you will deduce that it is something one-dimensional which should fit into this picture. But you can set without knowing anything about orbifold cohomology. You can just say, take the naive nth cone and add the divisors getting contracted. This thing define you a cone. And this cone fit together into this fan. So at least you see in this example, this fan as this kind of A model interpretation is indeed the Keller moduli space, like the various Keller cones of various chrepant resolutions, eventually completed by these bogus cones when there is divisorial contractions.
So my question was, what is it a Keller, special Keller manifold?
Sorry?
So
Is it a spatial Keller manifold? I think by, yes, by standard toric mirror symmetry, there is a spatial. I don't, in this example, I know there is a.
Is this naturally a special Keller structure?
I mean, I don't know from which point of view, but there is so much known about mirror symmetry for local P2 that I know there is a way, there is a natural, I mean, like the general 0 Gromov-Witten theory of local P2 will define you for you a spatial. I mean, actually, maybe on the B model side it's easier. Yeah, so the B model side, the periods, like essentially what Michel was describing, essentially the periods of these geometries will define for you some something like a spatial geometry. Yeah.
Well, because special Keller geometry of this type is classified, the 14 type as well.
Uh-huh. Oh yeah, I don't. Maybe this thing is like, does it matter if it's kind of non-compact Calabi-Yau?
That was the question. Yeah. It's compact case.
Ah.
I mean, special Keller is just special Keller. I mean, if you complex the moduli of the compact Calabi-Yau free.
So I need to be careful. It's not spatial Keller in the like compact sense. It's spatial Keller in the kind of non-compact sense. I don't know what are the correct words, but definitely in like in physics language there is something called rigid spatial geometry, which is what is relevant for non-compact. Like you need, yeah. But this thing has a natural structure you expect for families of non-compact Calabi-Yau.
But you can have a Keller in the
Probably, I think so. Yeah, I think so.
So I have another question, which is, you taught us that the generic fiber corresponds to the YDL, right?
Mm-hmm.
Now, so this since you identified the B multiple life spaces of both YDL and Z, so that means you probably want to identify the A multiple life spaces of the general fiber with the one of we're describing here. Is that correct? Or maybe my question is.
Yeah, I mean here it's not just the moduli space of YD. Here it's just the moduli space of YD plus epsilon C, where C is moving.
Okay, so yeah.
So there is not a moduli space of just YD without the divisor. Or in this context, you will suppose you will say this moduli space is a point because the toric right, and which will be compatible with the fact that in the general fiber of this thing will be like C star squared. And yeah, we'll need to think, but But in the non-toric situation, there will be a version of your question which I think is much more interesting. Like when YD itself has some kind of complex deformations.
Yeah, so I'll be curious
Mm-hmm.
to ask that question when we get there. Thank you.